work about interface is quite orthogonal to the rest of the conference, but I try to show that we are in connection. It is a work which is not alone, but with a long list of collaborators. So I begin by President Marseille is here, and the distance is the same than from Marseille to Béjaïa than to Marseille to Paris, I think. Okay, so we are the oldest city in France, and we have the sea as Béjaïa. Okay. Is a city founded by Greek people. So Aix-Marseille University is quite known university, and we are we can say that we are the first Francophone university in the world. Okay, but we have a lot of PhD students and so on. We have about 100 in the classification in Shanghai, and I am from a laboratory. The name is Laboratory of Mechanics and Acoustics, and it is a research unit together from CNRS, Aix-Marseille University, and Central Mediterranean. And we are about 140 people, and we are on two sites. The M site on the Marseille and the secondary site on Aix-en-Provence. My group is material and structure, but we are more on structure than on materials, if you want. We are not chemists, we are mechanicians, engineers. And we are working on scale chain, contact friction, adhesion, which is the theme of my talk today. We work on multiphysics couplings, on structure, on composite, and we have a lot of application on nuclear environment because we are close to the Cadarache, which is a big center of nuclear power. And we work on aeronautics and space because we are close to Airbus. And we work too on civil engineering on railway too. Okay, there are some application. I pass on the device that we can use, but the typicity of my group that we are connected between mathematics, numerics, and experiments. So we have at least 2 mathematicians in our group. We have physician and so on, and engineer. And the keyword of the talk is the damage in interfaces. So I have a long list of slides, but I can pass if I am in late. Okay. So the plan of the presentation, some motivation. I will present a general methodology for the modeling of interfaces. I show how to introduce damage in the model. How to introduce stochastics. I will finish by a short conclusion. So the motivation, we were interested by bonding problems. And in particular, we work with industry on offshore platform and on wind turbines. And the idea on this kind of platform, which they are floating platforms made in concrete, and there are a lot of structures that are bonded on the concrete. In particular, berthing structure, RTNL ladder, and so on. And the idea is to replace the bolted junction by bonding. And it is necessary to study the ultimate strength, the damage, and the edging, because the idea is to have this kind of structure during, I don't know, 20 years, 30 years. And for the beginning, we have developed model, but we have developed experimental tools. So there are different kind of experiments. We work on the adhesive, the glue as a material, okay? Epoxy, polyurethane, and so on. We work on glue as adhesive. So as a junction between two parts of here, there is aluminum or steel. And the third study is on structures. Here we have a structure in concrete bonded by with steel and bonding with a particular glue, which the name is Cicadir 30. And we are able to have tensile shear test, and torsion too is possible too. We have edging oven to study the edging of the glue, and we can use image correlation and X-ray image correlation to have a good approximation of the strain, and X-ray to have a good approximation of the porosity of the material, for example. And we work too on thermal and thermal aspect and vibration, because thermal is very important, and vibration too, because in the context of marine environment, there is a change of temperature and there is a lot of vibration due to the sea. And we have studied, here I present a study with six kind of glue, but in fact we have worked with I think 11, and 3 kind of environment. In still water, in seawater, Mediterranean seawater, and only with humidity, dry if you want. So it is the kind of result that we can obtain. There is an example of edging. So we have a lot of experiments, and we can take for example, 3 or 5 samples at each day here. For example, we have here there is an ultimate stress. So we use this kind of structures, and we have a tensile test, and we can try to obtain, for example, depending of the temperature, we have 3 kind of temperature for this Cicadir 30 in distilled water. And we can observe that after, I don't know, 1 year, we have a figure like this. So we have a decrease which is quite exponential of the ultimate strain. So the same for the rigidity of the structure. Okay, so we can use another glue, Loctite, in distilled of seawater. We can obtain this kind of curve which is very close to the Arrhenius law. Here we have the temperature, and here we have the number of days, and we obtain a line which is classical. Okay, and so we can determine at the temperature of the environment, we can determine the life of the glue. Another kind of results for densities for 6 adhesive, we can compare 6 adhesive. We have the datasheet value given by the industry, and we have different kind of experiments. We have 3 kind of experiments using pinometer, densitometer, and here is only with the mass. And we can compare the six glue which are epoxy, we are polyurethane, and so on. And we can compare for the density. We can do the same for the thermal conductivity for the 6 adhesive. Here there is only with these 3M that we have the industry results, and we have 3 experiments that to compute this, and we can observe that the Cicadir is very different for the other one for this parameter. Okay, and if we want to have a thermomechanical model, it is very important to have this kind of parameter. And we have another experiment. It's an experiment in vibration, because we are in laboratory of acoustics. And it is possible, we excite the sample here, which is a disk, and we can observe using Fourier transform the resonance modes, and we can compute these resonance modes using finite elements. We can compound, and we can deduce the rigidity, the Poisson ratio, and so on. And so we can do that. This is the experiment. We use a laser to measure. There is a piezoelectric materials for the excitation, and we find the modes. Here there are two resonance peaks in compression. Here in this zone and in this zone, and we can compare the experiment with three samples for each experiment, and we can compare with the numerical results you obtain with finite element. Okay, for the 6 glue. So now I will present the mathematical modeling. Okay. Sorry, there will be some equation in the future. So there is an evidence for this kind of problem. There is a small thickness of the glue. When we use a structure like that, which is a sample, but is not a real structure, but in a real structure is quite larger, that we have, I don't know, thickness of the glue which is 1 millimeter, for example, and we have the thickness, not the dimension of here it is aluminium. The dimension of aluminium is, I don't know, is 20 centimeter, for example. So we have a small parameter. Here there is a Cicadur 30, there is Loctite in this case. And we observe the same, that the blue is less than the aluminium or the steel. So when we have a small parameter, there are at least two possibilities to treat for the structural point of view. Here we want to compute a structure, okay? We don't want to compute the local effect, okay? We want to compute, in particular, the total structure. For example, it is possible to use, there are two possibilities when we have a small parameter, which is the thickness. So we develop adapted numerical method. It's possible to do that. Here we have an example of adapted numerical method. The refinement of the mesh is done by the exactitude of the solution. And the second way is to use simplified models. The simplified model says that we don't take into account geometrically the interface, the glue, but only the effect of the interface. It is the idea. So we obtain imperfect interface, that is to say that we have some jumps in the displacement or and in the stress vector. So we have some kind of models at the end. We have model which is very close to spring models, but we take into account this kind of jumps. So in the simplified model, there are two ways. The first one is to use phenomenological models. So we proceed only to experiment, and we try to be close to the experimental data. And the idea in my group is to use micromechanics to obtain deductive models. So we start from the microstructure, not at the chemical scale, but at the scale of the continuum. And we consider this thin layer as a small parameter, the thickness, and perhaps there are another small parameter, which is the stiffness. It's possible to do that. So we are at the micro scale. Here we have, for example, a wall, and we observe at the intermediate scale, and at the micro scale, we have this kind of material, which is the interface between between the bricks and the mortar. And we want to take into account all the effects that we have in reality. So the behavior of the interface, the materials, the presence of crack, the presence of roughness, the couplings with other phenomena, the temperature, and we went to take into account all the effects. So the methodology is the following. So we consider a patatoid, mechanical patatoid, if you want, in here, with the glue in yellow, and we have in this interface, which is the glue, we have a constitutive equation. The constitutive equation is given by the stress, the pure stress, the deformation, the strain, and so on. Okay, it is a relation like that. At the end, we want to, when this parameter epsilon tends to 0, we obtain a line, not a volume, but only a line. But we want in the interface, now it is an interface, we want to have a constitutive equation. We take into account all the effects that are in the interface. So, for example, the stress, the pure stress, the strain given gives the jump in displacement, and so on. And the difficulty using this kind of methodology is always to preserve the mechanical characteristic of the interface. Mechanical characteristic, but perhaps thermal characteristic, and so on. Okay, piezoelectricity if you want. Okay, so 4 recalls. Okay, and after that I can conclude. There are different kinds of interfaces. This is a tentative classification. In fact, what is important is the ratio between the stiffness of the glue and the stiffness of the adherent versus the thickness. So, in the case, for example, we want to use araldite and to bond plexiglass. In fact, the stiffness of the araldite and the stiffness of the plexiglass have the same order. So P is equal to 0. In the case of we want to bond with epoxy 2 pieces of steel, you obtain in case the epoxy is less stiff than the steel, and so in this case P is equal to 1. We have a soft interface. And it is possible for the welding to have P minus 1. That is to say that the glue, in fact, is more rigid than the material. Okay, so a second recall that there exists in the literature a long list of mathematical models, but really mathematical with a theorem, and in general you obtain this kind of law. The law links the traction vector between the width, the jump in the displacement. So you obtain some kind of result which is close to a spring, a nonlinear spring, in fact, because the nonlinearity is in this beta bar. And so you obtain a general spring. It is a classical imperfect interface. It is possible to obtain the same kind of result with hard interface. You obtain in this case a perfect interface at the first order, and the following order you obtain a jump in the displacement and a jump in the stress. And so you obtain non-local model because there appears tangential derivative. So the idea to compute to obtain the model, there are 5 steps: the expansion of the displacement of the stress in the term of thickness. After that, the rescaling, we change this geometry by this one in order to the dependence in epsilon in the thickness of the geometry in thickness avoids. And here we proceed to analysis on this configuration. The matching correspond to, in fact, what is the law between the adherent and the adhesive, and at the end you obtain a model. Okay. In the following, the n, the normal is E3. Okay. So I can pass on the case of unilateral contact, because it is one of the problems using this kind of methodology. there is a possible penetration between the two adherents. It's not good. Okay, it is possible to avoid this kind of problem. So I show now how to introduce damage. A possibility to do that because we have a spring model. It is a model like that. And if you proceed to some experiment, here you have a cyclic experiment. So loading, unloading, loading, unloading. At the end, we have the failure points. And we can observe that the line is not the same, in fact. So there is a damage in the materials. So the idea is to that a parameter of damage, the stiffness of the string depends on the parameter of damage. Okay. And to do that, an idea is to use to introduce micro cracks and in the glue using homogenization. For example, there is a long list, a long bibliography of how to introduce micro cracks in materials in order to obtain homogenized materials. We use this kind of materials, and after that we can proceed using asymptotic expansion. And so we have to add an evolutive law for the damage because the damage depends on the loading. So there is a free energy, the classical free energy, introducing a threshold because the damage doesn't start at the starting of the experiment. There is a time of threshold, and after that you obtain this the classical constitutive equation. The stiffness depending on the parameter of damage. We introduce a pseudo potential of dissipation, okay, and we obtain this kind of evolution law, which is very general, and in fact the evolution of the damage depends on the energy. Here there is a term of energy. And we can add some terms for non-locality and so on. And here we have the threshold, okay? So when this term is lower than this, there is no damage, okay? So after that, we can use this methodology to work on hard interface. We obtain something which is quite complex on the terms of on jump in displacement and jump in stress. And we have this kind of evolution law, which is depend, in fact, on there is a jump in the displacement along the interface. And here there is not the jump, but the average of the derivative. So you obtain some tangential terms. The methodology for soft interface for me is quite more interesting. So we have this kind of thickness which depend on epsilon. We obtain the classical spring, and after that you obtain at order 0 we obtain this kind of law. And in fact, at the interface, on the interface, you obtain here there is an energy of spring. And we have to compare to the threshold, and so we can proceed to the identification of the parameter because there are some parameters in the model, and we can compare here with an experiment in the literature with due to Murakami. It is an example very particular. It is an example in torsion and interaction together. Okay, we have a tube. The two parts of the tube are bounded by a glue, and we have a torsion and a traction. And you use two kind of model to introduce micro cracks. There are two possibilities, at least two possibilities, and we can compare the evolution. In fact, here we have the shear stress, and here we have the shear strain. And we can compare with the experiment. The experiment are in black, okay. And we have the two model we use here for two rates of loading. Okay. So the partial conclusion of this They say that we have, it is possible to use constitutive equation for the materials and kinematics to introduce. I have shown how to introduce cracks, but it's possible to introduce ruggedness, a small ruggedness in the model. I show how to introduce damage. We use asymptotic expansion. We obtain interface law, and after that, we have to solve the problem using finite element method. This example is obtained using finite element method. Okay, to compare the experimental solution with the numerical solution. Okay. I give one word on the stochastics. It is possible to introduce two stochastics because, in fact, the idea of the introduction of micro cracks, the micro cracks, it's very simple. It's a line in one direction. But if we look at the local level, we can see that, in fact, the length and the orientation of the crack, it's quasi stochastics. The thickness of the glue is not constant. The stiffness of the material is not constant. In fact, the stiffness of the glue is not constant. Depends, in fact, of the users. And okay, and the threshold, the viscosity, and so on, they are not constant. Finally, they are depend on the local aspect. And so we have a lot of uncertainty on the definition of the material. So the idea is to introduce Ito integral. I don't give you what is the Ito integral. It's a stochastic integral, and we replace the derivative, the weight of the damage by this kind of result. And here we have a Brownian motion. Okay, we introduce a Brownian motion in the equation. And we replace, in fact, here there is a pseudo potential of dissipation, and there are at least two possibilities. If I introduce the Ito integral in this term or not. Okay, so there is at the end there are two different models. And I don't show you how it is possible to solve the problem. It's quite technical, but the idea we proceed this kind of problem in 1D. We have here the adhesive, which is with the thickness, and the length is the adherent. It is a bar, and there is a loading which is dependent on time. We can compare, in fact, the deterministic solution, and we can compare with the two possibility in a stochastic solution. And we observe that one is more rigid than the other one, if you want. So it is the idea now. It is to see if it is possible to observe this at the local level to see if the good stochastic model is the yellow, it is the green. Okay, so on a more complex example, this kind of structure, and here the glue is here. Okay, and we can observe, in fact, for example, H is the value of the stochastic effect, and we can observe that without stochastic effect, with a small stochastic effect, okay, we have the same result. Okay, and it is necessary to introduce a quite great stochastic effect to have a divergence between the deterministic. Okay, and we can compare the two models, the 3D models and the 2D models. In fact, we are in 2D here, so there is a 2D model with the glue and a 1D model with only the interface. And we can compare the two results, and we can see that, in fact, that we obtain the same. So that is to say that asymptotic expansion is quite good. Okay. Okay. So as a conclusion, we have treated a lot of phenomenological model and asymptotic model. We have introduced damage. Now we know how to introduce damage. We have introduced unilateral condition. We have implemented the model in COMSOL, and we can now treat various kind of problem. the necessity is only to have some experiment to know better the glue, in fact, because each problem depends on the quality of the glue. And it is possible to introduce the various effects, elastoplasticity, the fact that the interface is not a plane but is curved. It is possible to introduce temperature, to introduce dynamics effects, and to introduce finished strain, because I have present only with small strain and a small smoothness and to viscoelasticity. And now in progress we have a lot of experiment to study, in particular how introduce edging in the model, because the model very present don't take into account the effect of edging. To better know the stochastic effect, and it is possible to introduce non-local effects, because experimentally we can see that there are some non-local effects. Okay. And thank you for your attention.